Hello, can you hear me? Hello, can you hear me? Hello, can you hear me?
Shankar, can you hear me?
Yes, I can. Can you hear me?
Yes.
Okay,
Both.
good.
So can you hear Venkat?
Hello, Venkat.
Yes, sir.
Yeah, how are you? How are
So
you?
you should use. Bring that here. And we will share it whenever.
Yes, sir. I'm good. I'm good. Sorry,
Yeah, good.
there's an. Oh, sir, what happened to TV? Just a minute. Just a minute, sir. Oh,
I can hear you. I can hear you.
just a minute,
Can
sir.
you hear me? Yeah.
There seems to be a problem. I should not. Yes. Is it audible, sir?
Yes. Am I audible
Okay.
to you?
Yeah, you're audible. Yes, sir.
Yeah. Okay. Okay. So you are in the God's own country, right?
Just a minute, sir. Yeah. Oh, can you say something, sir?
Hello. Can you hear me?
Oh, yes, we can hear you, but not through the TV. Yeah, we are trying to make it work. Yes, sir.
Okay.
Just
Okay.
a
Okay.
second.
Yeah. Yeah. Yeah.
Hello. Oh, we don't know whether it's coming to that. Okay, okay. Yes. Audio? Okay, yeah, maybe. You can. No. This is causing the issue. I don't know why. Audio, yes, sir. Maximum audio, yes, sir.
Last moment, everything goes wrong always. So let us give it few minutes. So it's only 3 of us. Huh? It's okay.
Shajesh, can you hear me?
Yes, I'm just giving it a few minutes just
Yeah,
in
no
case
problem.
someone is getting delayed or sometimes they don't know the Zoom room. It's not
Yeah,
like
no
walking
issue.
into a room, right?
Correct, yeah. I just want to check if I can share my slides.
Yes, sure. Go ahead. Share the slides. Use this. You. I don't have. No. Yes, Shankar, it's working. Yeah, I can see your slides. Maybe you can make it full size, I think, and
ആടെ ഒരു പൈസ കൊടുക്കേ കളരിയിൽ നിന്ന് തന്നെയെന്ന് പറയാം. I don't think you have the ability to mute them. You can mute them. Did I log in first? Did I log in first? Does it matter if you log in? Hello?
yeah.
Yes, I am already muted.
Yeah, could you go? We can hear your background. Maybe it will help if you mute.
Okay. I think
I'm not
leave
able to
and
mute from my side.
leaving and rejoining. Okay.
Yeah, it seems it's okay. Yeah, it's good. Thank you. Great.
Shajesh, are you able to see the full screen?
Yes.
Okay. Yeah, thank you.
Yes, so I think without further delay, I think let me.
Yeah, no issue.
Begin. I can introduce you from the. Take a look at. Maybe you can put on your video for a minute.
Yeah, no issue.
Yes, so we have a guest speaker today in general. Again, this is Sphics Science Center, and we are trying to organize some lectures here. Thank you all for attending. And today Sankaranarayanan from Untitled will speak on rolling objects. Welcome. Thanks. Go ahead.
Shall I start?
Yes, please.
Okay, I hope I am audible to all of you, and you can also see my screen, right? Full screen. Am I audible to all of you?
Yeah, we can hear you and we can see your screen.
Yeah, okay. Thank you, thank you. Well, it is in fact, it's a pleasure for me to be part of this series, lecture series in theoretical physics, initiated by my dear friend Shajesh. And my association with Shajesh is a very long time, and I'm connected to him after many, many years. So I'm really thankful for his for this opportunity, and I also congratulate Shajesh for creating such a platform for a beautiful informal interaction, especially for the target audience of young students, school and college students. So I wish and hope this initiation by Shajesh will go a long way, and he also has a center at near to his town where people can come and interact and so on. So in that way, I'm really glad. I wish the Sphics Science Center, initiated by his team, will have a very many events and days to come in the days to come. Okay, so myself Sankaranarayanan from NIT Tiruchirappalli. Today I will be discussing on the topic of rolling objects. Of course, it's a very elementary subject, and I know there are experts in the participants, and you have to pardon me because it's going to be a kind of learning, relearning, and so on, right? So we always learn and again. When you learn again and again, we enjoy the taste of science. Okay, so it's all about Newton's law of motion and nothing more than that. We need to revisit the Newton's law more than once on whenever you come across any scientific phenomena. Okay. So what are the rolling objects? So the rolling objects, when you say these are the objects which come to your mind, the solid sphere like iron ball or marble. You can also think of a hollow sphere like a ping pong ball. You can also think of solid cylinder, something like iron rod. And you can also have a hollow cylinder like pipes. And these are the objects which have a regular shape. So they can roll very easily and they will undergo a perfect rotation, right? When you allow these objects to roll over a slanting surface, they will make a perfect rolling. Of course, we assume that the surface is fairly smooth and so on. In such situation, these objects undergo a perfect rolling. Of course, if you have more complicated objects like irregular shapes and non-smooth surface, you will have more complicated rolling motion. But we are not talking about those complicated rolling motion. Rather, we will try to learn something from the simple, regular, or perfect rolling motion. Okay. So, in fact, I would like the participants at the end of the lecture or after the lecture, I would like the participants, at least the young participants, to do the experiments to review what has been discussed in this lecture. Okay. So Let us take a simple examples of these objects. You know, you have a solid sphere. So what I have shown here is a metal or iron sphere of different size. We also have marbles of different shape. So all are spherical in nature, smooth spherical surface. You can also think of hollow sphere as an example, ping pong ball or any other ball of different size and shape, different size, I'm sorry. And the third object is we are considering solid cylinder, which could be any rod, iron rod. So here I'm showing two examples. One is actually the iron rod of some length and some radius, and here you have the aluminum rod of different length and different thickness, right? And in the last, I am also having hollow cylinder, so something like pipes. So you have hollow cylinder here, which is made up of iron, and here on the right extreme, I have aluminum cylinder, which is made up of aluminum, and the middle I have a plastic. Okay, all are of hollow cylinder. Okay. Now, if you allow these objects to roll, we know what will happen, right? They roll from top to bottom, right? So we want to see how these objects are going to roll, and do we have any interesting phenomena happening, or essentially we want to understand the rolling motion of these objects. So we can ask many number of questions. Like for example, if I take a sphere of different size and different material, will they roll together? Will they roll with the same acceleration or not? Similarly for the other objects. Similarly, you can ask such questions for solid cylinder and hollow cylinder. Whether this rolling acceleration, whether it depends on the material, depends on the dimension, and depends on the shape. So these are the kind of questions we are asking. Of course, all these objects can be easily tested in our home, right? So that's what I want you to do after this lecture. I want you, the young participants, to try out this after this lecture. Okay, let us look at these objects, the motion of the objects from a simple example with a simple schematic diagram. So as I told you earlier, we are concerned with the so-called perfect rolling, where we are bothered about the rolling of regular shape on a smooth surface, wherein the object undergoes rotation and translation. It's something like this. So you have a slanting surface. Assume that this surface is a smooth surface, and I'm going to roll these objects which I have just shown. So, of course, the rolling is happening in a three-dimensional space, but for the simplicity of a schematic picture of what's happening, I just represent all these objects by a simple circle, right? So we just want to know how these objects are going to roll down. So when you think of these objects in a two-dimensional plane, we can represent it by a circle of radius r, right? This circle is going to roll down, so it will have a linear motion to a down. In addition, it will also have a rotational motion, right? So it's a translation plus rotation. Shajesh, am I audible to all of you?
Yes, I think that is to be very audible.
Okay. Rishikesh, how are you?
Yeah, audible, Shankar. Are you able to hear me?
Yeah. Thank you. Yeah.
Okay, yeah, you're audible.
Okay. So this object will undergo translation and rotation motion, right? So we want to understand this motion. In order to understand this translation and rotation motion for this simple situation, we need to understand what are the forces acting on this object, right? So what are the forces acting on this object? Obviously, the one force which is acting on the object is the gravitational force, which will try to pull it down, right? So if m is the mass of this object and g is the acceleration due to gravity, which is G. So the force is M times G, which will be pointing to the down. That is one force which is acting. Right. In addition to this, you have the smooth surface. Even though it's a very smooth surface, that smooth surface will definitely have some kind of friction. So that friction will exert a force in a direction such that it will tend to resist the motion, right? If the object tends to move forward, the friction will be acting in the opposite direction, right? So these are the two forces acting on these objects. So once you figure out all the forces acting on the object, you will be in a position to decipher what's happening to the object. Okay. Okay. So in order to understand more in detail, let us draw this direction of the forces acting on this object. So here I have these pictures with the forces and their direction. Of course, we are going to talk about many quantities which are vectorial quantities, but for simplicity, I will not bother about the direction, except that I understand where the forces are acting. But beyond that, I will be discussing mostly in the without bothering about the direction of the quantities. Okay. So you have this slanting surface which is actually having an angle phi with respect to the horizontal plane. Now you have this object. This object, as I said, it will have a translation as well as rotational motion, right? So here, this is the center of this object. So you can say we always have to have a correct understanding of center of mass for any object when we talk about dynamics of any object. So for this simple geometries, I can think of this as the center of mass. Okay, so this is my reference point. So at this point, the gravitational force is acting in this direction, m times g, where m is the mass of the object. And this mg, this is one force, and then you also have a frictional force over here, right? You have a frictional force over here, which will be acting in this direction. So which will tend to resist the motion. In addition to this, there is also a force which I forgot to mention, which is actually the normal force. So normal force will always tend to be in this direction. Okay. So now you have this mg, the normal force, and the fr. These are the three forces acting on it. Now, if you take this mg and this will make an angle theta with respect to this line. This line is in fact perpendicular to this slanting line. So obviously this angle will be theta, because this line is the mg, the direction of mg is towards the down, and this line is perpendicular to the horizontal line, and this line is perpendicular to this slanting line. So if this angle is theta, from the elementary geometry, we know that this angle is also phi, right? So if you take this mg into component on this direction and this direction, so there will be a force component which is mg cos theta in this direction, and there will be a mg sin theta in this direction, right? And here what happens is that this mg cos theta will be balanced by the normal force. So mg cos theta is going down, and the normal force is going in the opposite direction. Of course, normal force is a very, very tricky force to understand, and I recollect what Shajesh was discussing in the previous lecture. He gave a beautiful discussion on the normal force. So let us not go into the detail of it. So what happens here is that this mg cos theta component of mg will be exactly cancelled with the normal force, which is in the opposite direction. Now, what is left out is this force and this force. So mg sin theta will try to pull the object down, and the frictional force Fr will tend to push the object backward. Of course, the point at which this force is acting is only at the point of contact. That you have to remember. Okay. The mg sin theta is acting throughout the object, but the force Fr or the frictional force is acting only at this point. Okay, and in order to understand this object, this motion further, let us take a point on this circle, which is denoted as a black dot, right? So as you see here, as this object rolls down, you can see that this object, this red spot will actually have a linear motion because that will not make a rotation. But on the other hand, if you take this, the black dot on the circle, that will make a rotation, right? So we need to understand how this point is going to move with respect to time. And if you have any doubt, you can stop me and you can clarify if anything I need to clarify. Any questions?
Yes, question. Most of the discussion you're having, does this depend on a reference frame, like we are sitting on the wheel, or is it outside? Does it matter? Just curious.
Okay, we are just outside.
You're outside, right? Yeah, that helps.
Yes, yeah. I'm not sitting on the wheel. Yeah.
Correct. Yeah. Thanks.
Yeah.
Yeah.
Okay. Yeah. Okay. So having got the direction of all the forces acting on the object, now we can do a little bit of mathematics to understand what's happening. So what I'm going to do is, first I want to understand what happens to this dot. So this dot, actually the black dot will make a rotation in this direction. So let us try to understand this angular motion of this black dot. Okay. So let us take this red dot over here, which is the center of mass, and I have a black dot, and these two dots are separated by a distance r, and r is the radius of this object, right? Now, as time progresses, this black dot will make a will be moving on a circular path, something like this, right? So when this black dot is going to make a circular path like this, it is going to travel a distance of s. That's what we call it as the arc length. So over some time t, it will go from here to here. When it moves from here to here, it is going to take an angle of theta, right, with respect to the initial position. So this is the angular displacement, and this is the actual distance it has traveled from here to here. So obviously, as it moves, this theta will be a function of time, and so s will also be a function of time, right? So with this, we have a simple relation between s, r, and theta as follows. S is a function of time, and s of t is nothing but r times theta of t, right? S is equal to r theta. S is the actual distance traveled by the object, and theta is the angular displacement of that object or point, which is what we consider. Now you just take a derivative of this function, this quantity. You have a ds by dt, which is equal to r times d theta by dt. Yeah. So this ds by dt is what we call it as the v of t, which we call it as the linear velocity, right? So v of t is equal to r times omega, where omega is nothing but the d theta by dt, which is referred as the angular velocity.
A question,
So,
Shankar?
Yes. If you have a question,
Why
you
is
can
this
ask.
called the linear velocity?
Oh, well. So this black dot, it is actually moving on this path. In that, we are defining the velocity, which is actually the linear thing, right? It is a displacement, isn't it?
Okay.
Right?
Yeah, I think
It actually, yeah.
Yeah, okay, go ahead. I think just curious here.
Isn't it like that velocity is always supposed to be tangential to the path? And that's why it is called linear.
But this is true only when the wheel is involved, right? Because this is actually the velocity of the center when it is moving. but just for a point going in a circle, probably it is, I mean, maybe, I'm not sure. That's why I asked the question. I'm not very sure. Is my concern? Any comments?
Yeah, it
can
is
I
something like,
say something?
yeah, please, Rishikesh, yeah.
Yeah, so actually, basically, when this dot moves by, angular distance theta, then also you can imagine that because the whole wheel moves rigidly, right, as one object. So the other parts of the wheel also move on the surface. And if one looks at the linear distance covered by the center of mass, that happens to be this S. If it is doing a perfect rolling, then there is a one-to-one map between every point on the wheel and point on the surface. Okay.
Right.
So it exactly, I mean, there is a one-to-one map between every point when there's a perfect rolling. And that's why the amount of rolling length covered by the wheel exactly equals the translational distance covered by the center. So this V refers to the translational velocity of the linear velocity of the center of mass of the wheel. And it is related to R omega only when there is a perfect rolling condition.
Yeah, I think, yeah, thanks. I think that helps.
Yeah, that's
Yeah,
what's called
you are right,
linear
actually.
velocity.
Yeah,
Yeah.
yeah, that's fine. Yeah, exactly.
Suppose if it is not
So,
perfect rolling, then you will see that the mapping between the points on the wheel and on the surface on which is rolling is not one-to-one. For example, the wheel just spins at one point. Okay, then the same point are being touched by all the points of the wheel. Okay, the wheel skids, then you will see that the same point on the wheel touches many points on this thing. So the mapping is not one-to-one when it's not perfect rolling.
okay.
Maybe
Yeah, I
just
think,
a comment here related to my earlier question. This discussion has the reference frame as the center of the wheel. The earlier discussion had the reference frame outside the wheel. So that's probably the connection, I guess. Is that correct to say, Shankar?
yeah, actually, the point is in this rolling objects, we have a translation as well as rotational motion. So if you want to appreciate the translation motion of the object, we just look at the red dot, which is going to make a translation, right? Or linear motion. And the rotational motion can be appreciated by looking at how these black dots are moving.
Correct.
Yeah, sort of. Yeah.
Thanks. Yeah.
Yeah, I think Rishi's comment is also useful. It's nice that, as you said, there is a one-to-one mapping of this distance covering that much is covering on the plane, right? That's the linear distance it travels.
Yeah,
That's
yeah.
right. Yeah. Okay,
Yeah, that's why they are related. L is R theta. Yeah.
Yeah,
S is
yeah.
R theta.
Thank you. So we have this V is equal to R omega. Both V and omega themselves are functions of time. So if you take a derivative once again, you have a dv by dt, which is equal to R d omega by dt. The dv by dt is called as A, which is referred as the linear acceleration, right? So the rate of change of displacement is the velocity, and the rate of change of velocity is the acceleration. So A is referred as the linear acceleration. A is equal to R times alpha. This d omega by dt is now referred as the angular acceleration. Omega is the angular velocity, the rate of change of angular displacement, and the rate of change of omega is the angular acceleration, which is referred as the alpha. So we have a simple relation between linear and the angular accelerations, right? In this way. So this relation is going to be useful for our dynamics. Now, coming to this, the forces acting on this object, as I said earlier, there are two forces acting. One is the mg sine theta, which is actually taking the object forward, and you have a frictional force which is tending to resist the object, right? And this frictional force, which I call it as Fr, which is proportional to the normal force. That is the discussion which Shajesh made in the last lecture. Yeah,
Question, Shankar.
please.
This will be a static friction, correct? Because right at the bottom, it is at rest. And then we cannot, and it might be less than this also, right? Is it clear to us immediately that it is equal?
Yeah, you also discussed about the two cases, equal and less than that, right? The last lecture.
And only at the verge of movement does it become equal. So it is not, it's not clear to me that it is actually mu times n. And is that
it will not be mu times n. It can be any value between, non-zero to mu times n. Mu times n is the maximum value of the frictional force. And as it rolls, it is just F less than mu n. I mean, it can become mu n. It is, that's the limiting value.
Yeah.
But I think that is why probably you don't write a mu s or mu k in it. So probably it's realized that, yeah, it is something there, but it probably FR is sufficient.
Exactly. At this stage, you just write as FR.
Yeah.
Correct. Yeah. Thanks. Sorry for the interruption.
Yeah. So probably this is the maximum force you have, right? As you said.
Correct. Correct. Yeah.
Okay. Yeah. So we take this maximum frictional force, which is proportional to the normal force n, and the constant of proportionality is we refer it as the coefficient of friction. This coefficient of friction mu, it has all the information about the surface on which the object actually rolls, right? So this takes care of all the material property of the surface on which the object rolls. Yeah. Now, when this motion takes place, there is a torque applied on the object. Whenever there is a rotation, we call this rotational force sometimes as the torque or the moment of the force. So the torque tau can be written down as I times alpha, where alpha is the angular acceleration and I is the moment of inertia of the object. And this equation is nothing but the Newton's law of motion for the circular motion or the rotational motion. Okay. For a linear motion, we say linear force F is equal to m times A. And for the rotational motion, F is actually being replaced by tau, and the role of m is being played by I, and the linear acceleration is being replaced by the angular acceleration. Tau is equal to I times alpha. I'm not going to the detail of this expression, which anyway you can get it from the, there are very many textbooks where you can understand the moment of inertia, tau, and all that relation. So tau is actually I times alpha, and this tau is also referred as the moment of the force. If the frictional force is Fr, one can also write the tau in terms of the frictional force as Fr times R. Here again, the actual quantities are vectors, vectorial quantities. Tau is a vector, F is a vector, and R is a vector. But here I am not bothering about the directions, since since Fr is in fact perpendicular to the radial direction from the center. I just take it as Fr times R. Okay. Otherwise, it would have been the vector tau is Fr cross R vector. Okay. So in this case, tau is just Fr times R. So with these two relations, you have one relation where tau is written in terms of moment of inertia, and you have another relation, tau is written in terms of the frictional force. So these relations are now very useful for our purpose. So we can equate these two. Fr R is equal to I times alpha, with which you can write Fr as I alpha by R. Now we can make use of the relation which we got on the right hand side. A is equal to R times alpha. If you replace alpha by A by R, we have IA by R square. So this is a very useful relation here. Now we are writing the frictional force in terms of the moment of inertia of the object, the acceleration or the linear acceleration, and the radius r of the object. Shall I move on?
Yes, sounds good.
Okay. So now let's move on with this simple relation. So let us take this total force acting on the object. The total force acting on objects, as I mentioned earlier, there is a mg sin theta on the forward direction and the frictional force on the backward direction. So the net force is mg sin theta minus fr, which is the total force F. And this total force F is equal to m times a, where m is the mass of the object. As you know, this is nothing but the Newton's law of motion. The total force acting on the object is mg sin theta minus f, minus fr, right? So you just rearrange this equation. I can write this mg sin, sin phi. Mg sin phi is equal to ma times fr, which is equal to ma times ia by r square. We just got a relation that fr is equal to ia by r square. So we make use of that relation. We write it here. With this, you can write down this mg sin phi as ma. Actually, I take the ma outside. There is no m here, so I just multiply m and divide by m. So I can take this ma outside. I have ma times 1 plus I by r square, right? So with this, we have an expression for the linear acceleration of the object. When I say linear acceleration, what do I mean? Essentially, I am talking about the acceleration of the center of mass, right? Or the red dot. What is the acceleration of the red dot? The red dot is actually making only translational motion. Only the black dot is making the rotational and translation. So I'm asking the question, how quickly it is going to fall down. So the linear acceleration of the object is just a is equal to g sin phi by 1 plus I by mr square, right? So essentially, we got this linear acceleration of the object in terms of g, the gravitational acceleration, the angle phi, the inclined angle phi of the plane, the moment of inertia I, and the radius r of the object. So it's a pretty simple and useful relation for all these perfect rolling problem. Okay. Now we need to look at this expression and the result, and we need to understand what we can get out of it. So let's look at this relation. The linear acceleration of the object a is equal to g sin phi divided by 1 plus I by mr square. So what are the inferences from this expression? We can do it one after another. Okay. So the first inference is that if phi is 0, the acceleration is 0, right? That means the object will not have any acceleration at all, which means either the object will be at rest or it will be moving with a uniform speed. So a is 0 means the v is actually constant, right? A is nothing but the rate of change of velocity. So if a is 0, the velocity will be constant, right? If the velocity is 0, we say the object is at rest. If it has a non-zero value, it is moving with a constant, it is moving with a uniform speed, which is the case for a flat surface, all right? On the other hand, you see that this phi can vary from 0 to maximum, you can say, can take any value. Suppose 0, the phi varies from 0 to pi. Okay. If phi varies from 0 to pi, the sin phi also varies, it increases, right? So as phi increases, the acceleration a also increases. So we know that acceleration is more for steeper plane, right? And the third inference is that, more importantly, the acceleration a depends on the moment of inertia of the object I. Right? That's the most important thing here. So the moment of inertia of the object play a very crucial role in this kind of perfect rolling. So let us look at the last point more closely in the next slide. Any questions over here?
I think I'll wait until the next slide.
Yeah, fine. So let us look at the dependence of acceleration on moment of inertia more closely. I just rewrite the same expression which I got. Now let us look at this expression more closely for all the cases I have considered. So I have objects like solid sphere, solid cylinder, hollow sphere, and hollow cylinder. In the case of solid sphere, at the moment of inertia I, of course, when you talk about the moment of inertia, you have to talk about the moment of inertia about which axis, right? So here you see that this object is rolling, and when this object is rolling, the axis of rolling will be pointing outward normal, right? Outward normal to the plane of the computer screen. So with respect to that axis, what is the moment of inertia, right? So whenever you talk about moment of inertia, you should talk about moment of inertia with respect to the axis of rotation. So with respect to the axis of rotation, in this case, the solid sphere will have a moment of inertia I, which is given by 2 by 5 m r square. So you just substitute this value over here, 2 by 5 m r square, right? So m r square get cancelled off. So you have 2 by 5 here, which means 1 plus 2 by 5, which is 7 by 5 in the denominator. And finally, you get A is equal to 5 by 7 g times sine phi. So which is approximately 0.71 g sine phi, right? You can work out the same thing for other cases also. For the solid cylinder, the moment of inertia is 1 by 2 m r square. So wherein A is equal to, you have 1 by 2 m r square, that means 1 by 2 here. So the denominator you have 3 by 2. So which gives you A as 2 by 3 g sine phi, which is approximately 0.67 g sine phi. Similarly, for the hollow sphere, I is equal to 2 by 3 m r square, and we get A is equal to 3 by 5 g sine phi. So we get acceleration A as 0.6 g sine phi. Similarly, for the hollow cylinder, I is equal to m r square and A is equal to 1 by 2 g sine phi, which is exactly equal to 0.5 sine g phi, 0.5 g sine phi. You see that if you look at the acceleration of these four objects, so this is having the lowest acceleration, the linear acceleration, 0.5 times g sine phi. Of course, g sine phi is there in all the expressions. So this is 0.5, 0.6, 0.67, and 0.71. So what you see here is that this object, the hollow cylinder, will have a lowest acceleration among the four, and the solid sphere will have the highest acceleration among the four, right? So if you allow these objects to roll, you can conduct a race, right? So what will happen is that this will be the slowest one, and the solid sphere will be the fastest one, right? Yeah. So the most importantly, you see that this understanding we get from the understanding of moment of inertia. So crucially, the rolling crucially depends on the moment of inertia of the object. Of course, the moment of inertia depends crucially on the shape of the object, right? So
question,
yes,
is
please.
it possible to get less than 0.5?
I'm not sure.
Okay. And is there an upper limit?
Upper limit for I?
For yeah, I or
for
A
A.
actually.
A.
Like, is there any upper limit, or maybe can I be negative?
Oh, I don't think I can be negative.
Unless
m is negative.
Yeah, I agree. But then if it is negative, I was thinking A can really shoot up, but probably not. Yeah, I cannot be negative.
Okay, yeah. but I do not know the lowest value and the highest value.
Yeah.
I'm not sure.
Like I, can it be greater than the number in front of it? Can it be greater than 1?
Oh,
I,
uh,
yeah,
Oh, that's
even
a-
I don't know the answer. Yeah, I was just
I,
curious.
I don't know. Yeah, yeah. Okay.
And another comment, since this is a dimensionless construction, you make I over mr square. One
Right,
could
yeah.
ask, what if this were a fractal geometry, this object? Is there a non-trivial conclusion you can make in that, right? That's a, since it's dimensionless, I ask, and there is not much. It's a pure number there. One.
Yeah, yeah.
It might not
So
be a
is it-
relevant question, but still, yeah, just a comment.
Yeah, with your comment, I'm curious what will happen if you allow the fractional objects to roll?
Yeah, at least theoretically.
Sorry,
Yes,
sorry,
okay.
I didn't get what's the question, Shankar?
So the comment I'm making is that if I had an object which is like a Russian dolls, you say, right? A sphere inside a sphere inside a sphere, which will have a convergent I in it. But now let's do the opposite, where the weight increases and there is a divergent factor coming in for I. And then will these conclusion, at least theoretically, will that hold or not?
In
might
divergent
have
factor,
some-
meaning the, what is the value for I you're talking about?
Like, for example, let us have a, like, suppose I have I built out of concentric spheres, and it keeps going up and up. And let's say the masses are distributed in such a way that I get a series for I as 1 plus 2 plus 3 plus 4 and so on. And we know in some context that that number is equal to minus 1 over 12, which will give me a negative number for I. And then my acceleration will really shoot up. And there can be very counterintuitive conclusions there. But I can, it's seemingly I can build such arguments. Is that clear what I'm saying? So the way I'm building this is that I'm having a concentric set of spheres. The first sphere has an mr square equal to 1. The second sphere is, let's say, 2. Third one is 3. Fourth one is 4, and so on. So I'll get a series of the kind 1 plus 2 plus 3 plus 4 and so on. And immediately I would say, in some sense, some context, it's equal to minus 1 over 12. And suddenly I have a moment of inertia which is negative, which is meaningless in a sense. But at some theoretical level, I can do that. And
But so we have to see how do we compute the moment of inertia. That's where the whole trick lies, because ultimately, physically it has to be a finite positive number, because what does infinite inertia mean anyway? And you're talking about a Ramanujan series, right? Minus 1 over 12.
Yes.
But I think maybe perhaps the catch lies in our extrapolation to that series. Is I really expressible like that series? Because you have to actually compute the I, right?
Reasonable. Yeah, very reasonable. It's just a comment. I understand the issues associated with the physical interpretation, but at least at a mathematical level, there is some issue.
Mathematical level also, when you extrapolate, I, you have to compute that integral, right? For I. So that will have the, I think, intricacies which will perhaps, which will ensure that.
Yeah. Completely agreed, I think. Yeah.
I don't know. I mean, just.
No, it was just a comment. And since I talked about it just recently, it was fresh in my mind. And
But sometimes it's good, such comments, make us think harder, and these comments is what makes it interesting. Yeah. Thanks.
Cool.
Yeah, thank you, Shajesh, for giving such comments on the possibility of a moment of inertia being negative.
Yeah.
Okay. Yeah, it's very interesting. One can still think about it mathematically, as you said. Okay. So coming to this, the race of all these four objects, we see that the shape actually matters. And so finally, I just want to conclude by saying that the shape of the object matters for the rolling. And in this race, solid sphere wins. And more importantly, the acceleration of this object depends, it is independent of the dimension and material. It depends only on the shape, right? Whether you roll a cylinder of made up of aluminum or iron, the material doesn't matter, and the length or the radius doesn't matter. What it matters is only the shape. So that is the interesting conclusion we come up with in this simple example. And I would like to have, if, one can think of more interesting problems. As I see, what happen if the one possibility is what happen if you roll the irregular shapes and things like that? Is there any interesting thing happening if you roll the irregular shapes and things like that? Of course, for the irregular shapes, the A itself will not be constant, like what we have seen here. The acceleration itself will be a function of time. But those are more complicated things, I presume. There are some nice videos I have seen by Bruce Uni, where he showed rolling of objects of different shapes and so on and so forth. But they're all more interesting things to ponder about. So with this, I just conclude my lecture by saying that what we have to learn to do, we learn by doing. And thank you all for your attention. Now we can have more questions since we have time, right?
Yes, we have time. Yeah. Thank you, Shankar. That was very nice. I'll open it for questions at this point, please. Any comments or questions? Just feel free to ask. I don't think I have to really control it. It's a small.
Actually, I don't want to talk about the rolling objects on an incline, but if it is possible, I would like to have a discussion on rolling friction when it is on the flat surface versus when it is on the incline.
So what is rolling friction?
Well, any object that is rolling, but I mean, you guys commented already, right? The rolling friction is much lesser than any other friction that is acting between two objects. It's not a static friction. It is not sliding friction. Ideally, it is supposed to be zero, but normally the material, because of the deformation of the material, there is some slight rolling friction that acts between the surfaces. But it has a different behavior when it is on the flat surface versus when it is on the incline. And I think you must have talked about it in your talk, Shajesh. The car
I think
friction
we
on
have
the wheels
had
of
this
the car.
discussion before.
Yeah, but
I
I missed
feel
that
there
talk.
is
So
no such. I mean, probably what you mean is the force that acts on a rolling wheel is what you call rolling friction, correct? Is that your definition of rolling friction?
well, honestly, if you ask me, I'm totally confused with that. So
Yeah,
that's why
I
I'm
feel
asking, like, if anyone wants to, like, shed light on what exactly rolling friction is and why does it differ between wheel rolling on a flat surface versus when it is on an incline, I think would be nice. So it's slightly,
like, it's a good point to ask, like, don't we have an exact expression for the rolling friction in this case? Like what Prachi is saying is rolling friction. We have an exact expression in terms of acceleration, I suppose. And the question is, does it depend on the material properties at all? It probably doesn't.
rolling friction ideally is supposed to depend on the material property, even the property of the surface it is rolling on.
Like in this case, because it is constrained, it's it's related to the the maximum value is static friction. And, or my question is, can we have an expression for the friction in terms of, like we have static friction is μs times n. Is it possible to have such an expression in this case? Like there is no material property dependence in this rolling case. Am I right?
Well, in the engineering courses, we do give like a static, like rolling friction, a coefficient of rolling friction. And it is a much smaller quantity than anything else between those two materials. And the point is, like, rolling friction ideally is supposed to absorb energy away. So it is supposed to decrease or act against. While static friction, when a wheel is rolling, we never say that it is going to take away any kind of energy because no work is done.
So
But
there was an expression Shankar wrote, the rolling friction is equal to I times alpha over R. And alpha we got an expression for in terms of acceleration. So the friction depends on acceleration, not on any material property. Is that a correct conclusion to make there? Right, yeah, so here force of friction is I times alpha over R square. Alpha is related to A. So it's just, it does not depend on the material properties, I guess. Am I right? At least in this way of looking at it.
Ashish, well,
I'm just commenting.
No, I have a, so the point is that particular expression, the right hand side is the effect of the force. The origin of the force is somewhere else.
But acceleration cannot, acceleration can depend on, so you're saying force of friction depends on acceleration, but acceleration itself depends on.
No, force
but
is
just
not
now we
on
showed that
acceleration
the
or anything,
acceleration is only dependent on the geometry, not on the material properties. Like, does it matter whether the cylinder is built out of rubber or metal?
Shajesh, acceleration is an effect. Like there is a cause here. The cause is the rolling friction. Where is it arising from?
Yeah, but okay. So maybe the last slide of Shankar, where he had 0.5 G sine alpha. Does it matter whether that cylinder is built out of rubber or metal? Like, last expression 0.5 G alpha for a hollow cylinder. Does it matter whether it is built out of a rubber material or a metal material? I claim it does not matter, but I could be wrong. It's seemingly it is,
So I think here, because it has not yet attained the final value for the friction, the F here is still within the limiting value, mu times n. So when it, the material will determine the value of the mu. Okay.
But the moment you reach that value, it is not perfectly rolling.
Yeah, so because these all values are given for the case where it is still not, it has not crossed that value. It is less than that. So it doesn't matter.
But
so
the moment you reach that value, it is not perfectly rolling. So for the scenario we are considering,
if you cross that, even if you reach, that's not an issue. If you cross that, then there will be sliding. As long as you don't cross that value, it doesn't really matter.
Correct. So it doesn't matter, right? You agree?
Yeah. Well, as long as you don't cross that value. And by the way, Shajesh, you said about this, friction, perfect rolling and things slowing down. So when things are rolling, in your talk.
Oh, in my talk, I see.
Yeah, I'm because it's related to this, okay? It's related to what Prachi is also asking. So when, anything is rolling, the point of contact is never perfectly one point of contact. There is some flattening at the bottom.
Yeah.
Correct.
The wheel.
I agree.
Now when it flattens, No, I'm just trying to say that where does that slowing down come from? So when it flattens, the wheel presses on the ground harder.
Yeah.
So if you look at some, suppose some delta x distance it's a very small distance, but suppose the wheel makes a contact not at a point, but with the ground on a flat delta x distance. Okay. Now, when the wheel is rolling, suppose, in a say clockwise direction, so it presses. So the pressing of the wheel on the ground is not uniform on the floor. It presses harder on the front side. Okay. So the normal, because, as it comes, as it lands, the pressing is harder on the front side of the, so this is my index finger and thumb. Okay. This is the delta x. So pressing is harder on my index finger than on the thumb. So there is a normal reaction of the ground, which is not normally when there is one point of contact, that normal reaction is passing from the center of mass. Now, the normal reaction is slightly displaced, it is slightly away from the center of mass. So the mg is coming down and n is going, my right finger is n and this finger is mg. So there is a small distance delta x between n and mg. Now this n, which is a normal reaction, it applies a torque with a lever arm of delta x, and it is this torque due to the normal reaction which is not exactly passing to the center of mass, which actually slows down the wheel. So you have a perfect rolling and yet the wheel eventually stops. That is because no railways, with this iron wheels, because it minimizes the, so that the loss due to this normal reaction being away from the center is minimized, because the flattening is very minimal for a very rigid iron wheel.
Mhm. Yeah. But Rishi, I mean, I
It's
understand.
perfect rolling. I'm saying it's a perfect rolling, and yet you have eventually the wheel, because in the ideal rolling where there's only one point of contact, there is no loss, so it can actually even go on forever.
Yeah, so Rishi, I understand the practical aspect of it. My original question was related with, there is a difference in the direction of friction when you are on a flat surface versus when you are on an inclined surface. Both of them are rolling. And
Yeah.
And I think I wanted like a comment on that particular one, that, oh, why the direction actually changes. And it has like, it must be like a little bit related to whatever Shajish probably talked last week. But the point is, like, whenever a wheel is rolling and without anything else acting on it, suppose you have left it rolling on a flat surface, the direction of the force of friction is in different direction. And we always say, oh, the point which is touching the ground is static and it is going to go backwards. So the force of friction has to act forward. So on the flat surface, you always say that the force of friction is actually acting forward, while when it is an inclined plane, we always say it is acting backward. And that's the point I was wanting to like clarify.
Ultimately depends upon the, what direction the force is acting. Right. And you have a mg sine theta, which is trying to, okay, so imagine that, you have an inclined plane and you have a wheel on it and you have an mg sine theta. Suppose the inclined plane is like frictionless. Okay. And you have an mg sine theta, which is parallel to the plane and pulling it down. So it will have a tendency to displace the wheel on this surface towards the ground. The wheel will tend to slide if it is frictionless, right? It will tend to slide towards the ground.
No, I understand, but think about it now on the flat surface. Nothing is going, like the mg is going right from the point itself, directly downward, right? There is nothing which is going to make it slide or anything else. Why do we even bring in the topic of like there is a friction acting there and it is the friction which is making the wheel move?
So fine. So then you have to first tell me.
I think there is a comment being made.
Yeah.
Please, I think Anand or maybe 09. The number, I
Anand
don't know the name.
probably was saying something.
Probably it was just background noise. Sorry, I think Rishi, go ahead.
So then you have to first tell me that how do you bring it to roll first? Okay. You have a wheel rolling on the ground. So how did you bring it to, this rolling? How did you bring it to the rolling condition? Because suppose
Maybe,
if you first apply
maybe
a spin
Rishi,
and then put it.
I can make a comment here. Suppose I rephrase Prachi's question in the following way. While a wheel is rolling down, it is connected to an engine. So just the fact that the engine is making it roll down requires that the friction be in the forward direction. And the fact that mg sine alpha is acting, it requires the friction to be backward. I guess there will be a threshold here where one will take over. So it's not very clear to me in what direction the friction will act. Is that what you're pointing out? Maybe.
He's talking about the flat surface first that,
Yeah. I mean,
incline,
it is always very confusing to me because whenever, like in introductory physics, we bring the topic on the flat surface, we always say that, oh, the friction is the thing that is making it move forward. It is acting forward, right? Because you say that, oh, consider the wheel rolling. And now the problem is, like, I can understand the incline much better than I can understand the flat surface. Because on a incline there is, as Rishi said, like there is a force that can make it slide. So it has to resist that. Resist the sliding tendency of sliding motion. But I don't understand the flat surface at all.
So that in the flat surface also we need to ask as to what is it that first makes it roll to begin with. Suppose you first spin the wheel and then put it on the surface. Okay. Will it immediately start perfect rolling? Suppose you give a spin omega. No, right? Of course, it won't. There will be, some sliding. Okay. Then the frictional force will actually act in the, so suppose if it's sliding in this direction. Okay. So as it lands on the surface, this forward motion, it will hit on the floor backwards. The floor will hit on the wheel in the front direction. So the friction will point in the front direction and it will retard the spin until a point will come where the spin will be just right for it to roll without slipping.
And one can see this in billiard balls. You can actually.
So here is a question. Here is another question. The point is, when is it in the forward direction? Because eventually this wheel is also going to stop.
It will not stop.
In perfect
if it is
case,
not going to stop, then it is going
scenario.
to accelerate, right? Then it should continue accelerating.
No, in perfect scenario, it will just keep going. Excuse me.
Not keep going, keep accelerating, right? Perfect scenario.
No.
There will
If
be
you
no
say that
friction
it is
after
going-
it attains the perfect rolling.
Yeah, perfect rolling in a flat case, there is no friction. Yeah.
Once it attains the perfect rolling, but before it attains, okay, because it may not have the right omega, because the right omega is a function of the smoothness of the floor, right? So the moment you spin the ball and make it land on the surface, suppose you make it spin in a in a clockwise direction. Okay. So as the ball lands on the floor, it will hit the floor and it will tend to push on the floor in the backward direction. And the reaction force of the floor on the ball will be in the forward direction. Torque due to that friction, R cross F will be in a counterclockwise, so it will retard the omega. Okay. And it will slide until it will reach omega where it will roll without slipping.
So you are saying that in perfect rolling on a flat surface, there should not be any force acting at all, right?
Yeah.
Any friction acting.
Because you can imagine, Prachi, you can imagine that suppose, even if once it starts perfect rolling and there is still F acting on it, then it will decelerate.
Yeah, yeah,
stop it.
exactly. Like, I mean, it has
Right, it will
always
stop.
bothered me. Yeah.
Then
This particular
the
thing.
frictional, yeah, it will vanish. There will be no F after it starts, after it attains the perfect rolling.
Mhm. I see.
But again, it depends. Okay. So yeah, here is the thing. It depends if there is any other external force acting or not. Okay. Talking about putting things on a roll on a floor with friction being the only dynamical entity, of course, it will come into play for some time. And once the perfect rolling is attained, then the friction will not be there and it will go on with a constant omega forever. But suppose there are other external forces acting. Like, for example, that is the scenario with the cylinder or something rolling down the incline, because there is mv sin theta. When there are external forces acting, then of course friction will always be there, and the balance of friction and the external force will dictate the translational acceleration and the torque. Again, here I think I just wanted to make one comment that Shankar assumed that he's taking the torque about the center of mass, right? The torque due to friction is about the center of mass and it is making it roll. But one did not assume that. You can take a torque about any point. You can take a torque about a fixed point on the incline, or you can take a torque about the point of contact. In which case, of course, then you have to, of course, use the parallel axis theorem from moment of inertia. You can take a torque about the point of contact. mv sin theta will apply the torque, not the friction. So implicit in Sankar's derivation was that the torque is calculated about the center of mass, but you did not do that. Now it turns out that actually, one has to be wary of calculating the torques. Okay, either you take a torque about a fixed point, or you take it about an accelerating point. If you find a torque about any other center of mass, then you have to worry about, maybe I'll give a talk on this sometime, then you have to worry about the pseudo torques. If you are taking a torque about an accelerating point, okay, then you have to also worry about the pseudo torque and then find the, do the dynamics. Now it turns out that for a cylinder rolling on an incline, okay, although this point of contact is accelerating, but turns out that it still will not contribute to pseudo torque. Okay.
I think the point is that the axis about which it is rotating is not changing. If the axis is pointing in the same direction all the time, like in this kind of motion where translation and rotation is happening, if the rotational axis is fixed in direction, then your point is correct that it is independent of that. Otherwise, it is very frame dependent. Like,
You're right.
like
You're right.
Corioli. Yeah, I think
so. Yeah.
so.
See, when you say frame, I mean, we are typically always calculating things in inertial frames, typically. Of course, if you do it in non-inertial frames, then you have to use.
And,
okay, but
and the origin dependence also, here it is origin, like the axis dependence. Axis dependence. So if the axis is fixed, which is the case in the discussion we are having, then it is okay. It can be anywhere, but often
Sajesh, you can,
like a football being thrown is a classic example. Then it's too complicated, I think. The axis.
Sajesh, you can calculate torque about any point, right? You calculate a torque about a point, not about an axis. You can calculate it about any point. Now, whether the point is fixed or accelerating, that's the point that I'm trying to. Point.
Yeah, like.
Doesn't have to be on the axis.
Like my point is, again, I haven't done this things rigorously, but at least the connection between translation and rotation, when we write this is acceleration is equal to alpha times r, those connections are not so straightforward when the axis is not pointing in the same direction, then that rotation of the axis will play a role.
Oh no, no, oh, that is
Maybe,
okay.
maybe
I
that's
see
what I'm making.
I see. So okay, so there are several different issues. One is that
Probably.
you have a fixed axis rotation.
Yeah.
When you have an axis of rotation which is not remaining fixed and changing in direction, then of course you have to worry about the precision, nutation, and the whole lot. The top,
Exactly.
the motion of a
Yeah.
top, and that's whole lot more complicated.
Yeah, that's what I was
Saying that,
pointing out.
no, I completely. That's whole, the gyroscopic motion and all that. That's far more complicated. But even if you forget about that, you can do your torque analysis about any point.
Only
can
if the
find-
axis is fixed, correct?
Even
No?
for, okay, let us first say that we are talking about fixed axis motion, okay? Which means your axis, even in the translation axis, is not changing the direction, okay?
Okay.
Even for that, you are free to calculate torque about any point. Okay, you can.
Yeah.
It turns out that it is safest to calculate about center of mass because, interestingly, even if center of mass is accelerating, there is no pseudo torque contribution, even if it is accelerating. Okay, for example, if you do Newtonian dynamics, translational motion, okay, F equals ma. Of course, this statement is F equals ma is true only for the inertial reference frames, right? You are referring, when I say that F equals ma is true for inertial frames, what I mean is that the understanding of F as the real force on the LHS, the causative agent being the real forces. You can, of course, do this whole calculation in non-inertial frame as well. Once you take into account the fact that you are doing in non-inertial frames and take all the non-inertial terms, the Corioli force and the centrifugal force, everything you take into account, you can do a perfectly good job. And sometimes actually it's even convenient to do that in non-inertial frame. But when you are formulating F equals ma, your F there refers to real forces, right? And if you are framing your dynamical equation of motion in non-inertial frame, then of course there are pseudo force terms which you have to take into account to make things work, right? The mass times the acceleration of the frame minus m times a. Similarly, if you are taking a torque about a point which is accelerating, then you have to similarly factor in the pseudo torque, okay, for you to get the correct answer. Otherwise, you will run into troubles.
So here is a question I have. I mean, I'll be interested in this. Is that is there an example where the axis is fixed?
Yes.
But the contribution to this rotational motion is
Yes.
there is an extra term because of this pseudo torques. Like, what's the example where the axis is fixed? We are saying it's always in the same direction.
See, it has nothing to do. Okay. So,
is my question clear?
Yeah, I got your question very clear. Okay, you are saying that, can you give me an example where the axis is fixed and yet there is an extra contribution to the pseudo torque?
Correct. Yeah.
Okay.
Maybe it is
Now,
possible. I don't know.
Yeah. So, and if once I tell you the form of the term due to the pseudo torque, you will see that it has no reference to the change of direction of the axis. Okay. Suppose your center of mass is RCM, and suppose you are trying to calculate a torque about a point R0, which is accelerating. That point is accelerating. Okay. So the contribution of pseudo torque is R minus R0 cross M R0 double dot. Okay. RCM minus R0 bracket cross M R0 double dot. So now you can clearly see here that this term is 0 if R0 equals RCM, because it is RCM minus R0, right? So if R0 equals RCM, then of course this term will be 0, right? Or if R0 double dot is 0, which means your point is fixed, it's not accelerating. then also this term will be 0. Okay. And it's a cross product of RCM minus R naught and R naught double dot. So whenever the cross product vanishes, then also the pseudo torque will not contribute. But if you have any situation where none of this is true, okay, I think one of the Saturday I'll give a talk on this. And so it turns out that in the problem which Shankar has showed, if you look at, if you find a torque about the point of contact instead of center of mass, Shankar found a torque about the center of mass, right? Frictional force times R is equal to I times alpha.
Yeah.
Right. And of course, there is no torque due to mg because mg is passing from the center of mass. Right. Now suppose I say that Shankar, you do the same exercise, solve the same problem, but instead of finding torque about the center of mass, find the torque about the point of contact. So obviously friction will not provide any torque about the point of contact because friction is passing from the point of contact.
Correct.
Right. So does it mean that you cannot find a torque about any other point than the center of mass? No. There is a torque due to mg sine theta about the point of contact. Okay. Because mg sine theta is passing from the center of mass.
I think that problem is also done, Rishi, right? Like,
yeah, exactly. You
it
can
gives
do it.
you the same. It gives you the same result, right?
Exactly, same result. But now your I, because you are finding the torque about a point which is not the center of mass. Okay.
Yeah, your I.
The moment of inertia has to be different. It is.
Yeah.
You have to use the parallel axis theorem.
Exactly.
Moment of inertia about the center of mass times mr squared.
Yeah. Exactly.
Okay, when you do that, you get the same answer. Okay.
Yeah.
Now, what I'm trying to say is exactly what I'm trying to say here is that there is a subtlety here which is often overlooked. It turns out that this point of contact is actually accelerating. Okay. So, because if you look at the trajectory,
you remember that this is called the point, like instantaneous center of zero velocity.
Yes.
IC point, right?
Yes.
And you can do an analysis about an IC point, which we like normally do in the dynamics.
Yes. But I'm giving the reason that actually if you look at the trajectory of the point of contact, it's actually cycloid.
Yes.
Okay. So it doesn't have a zero acceleration. It is a non-zero acceleration. Okay. It has a non-zero acceleration. So ideally speaking, you should have a pseudo torque due to, you should do an analysis about that point. But it turns out that the cross product of RCM minus R naught and R naught double dot is vanishing. And that's why the pseudo torque doesn't contribute there. Okay. Analysis without understanding that the pseudo torque is
would it be correct? So wouldn't it be right to say that about any point this will be true? Like, or my question is the following: is there a acceleration was equal to 0.5 g sine alpha, right, for hollow cylinder?
Yeah.
Will this calculation have a different result ever in any other choice that we make?
No,
right? Not at all. Okay.
No.
But on the other hand, if we had a system that, suppose there was a cone that was rolling, and cone in such a way that, or somehow I want to move the rotate the axis around, then I can have a certain.
That analysis will be different, right, Shajish? Because direction of the axis is changing.
Yeah,
then you will have to take into account.
Yeah, then it is 2 off.
Yeah, that is a different. That's a different.
So I
problem,
think one
right?
has to come up with a better problem. Yeah. Okay. No,
but then
I'm fine.
cone is a different thing, right? I mean, we'll have to. The dynamically, it's different. It doesn't have the. When it rolls, it doesn't have the azimuthal symmetry of the cylinder.
Yeah. Okay. Yeah. Think.
Yeah. Can somebody throw some light on how to appreciate the pseudo torque on some real systems?
Shankar, actually, So it's, when we do any dynamics, be it say translational, you write F equals ma, implicit in your analysis of F equals ma is a choice of reference frame. Okay. So when you say that, so I mean, what is your interpretation of Newton's second law? When you say F equals ma, what is F? F are all it, and it's a vector sum of all real forces acting on a body, right? It's the cause, causative agent, and A is the effect of that cause. But cause, what is the source of cause? These are the real forces. It could be normal reaction, friction, tension, gravity, Coulomb force, real forces. Okay, that equals. But this analysis is true only when you refer this second law to an inertial frame. Okay. Inertial frame, what is inertial frame? Inertial frame is a frame in which any body which is free from any real influence, real forces, will be enjoying uniform rectilinear motion. So if there is any body which is on which there are no palpable physical forces acting, and if the body is enjoying uniform rectilinear motion, then that understanding of that motion is said to be under the inertial frame. Okay. But now, for some reason, and because there are no inertial frames, right? Inertial frames don't exist. There is no such thing as inertial frame. So every frame is to some extent a non-inertial frame. Earth, and Earth is moving around the sun, spinning out of the axis and all that. So now that you are using a frame which is not legally allowed by the second law, okay. So how do you formulate your dynamics in non-inertial frame? Okay. So when you formulate your second law in non-inertial frame, you will notice that if you want to write down the Newton's second law in non-inertial frame, then it's not just F equals ma, but it is F, which is real force, minus times the acceleration of the non-inertial frame that you are using, that equals m times the acceleration in the non-inertial frame. Okay. This is, but now this is just a vectorial equation. Okay. Now, if you tell me that what is this acceleration of the non-inertial frame? Is it linear acceleration or rotational acceleration? So suppose if you are doing it in a rotational frame, if the frame is moving with angular speed omega, it's a non-inertial frame, right? Then you have to, it turns out that this whole expression becomes far more complicated. You have extra terms known as the Corioli term and the centrifugal force. In fact, students often have a lot of confusion about this. In fact, they tend to think that, circular motion, there is a cancellation between the centripetal and centrifugal force. A lot of students, they from the +2 when they come, they think that centrifugal bahar lagta hai, centripetal is inwards, centrifugal is outwards, and that's why there is no net force on the body moving in a circle, and that's why it it doesn't come to the center. They are intuitively think that bodies move in the direction of force. Okay. So why the body is not coming to the center? Because the centripetal force is balanced by the centrifugal force. I mean, they have a very erroneous. I think it's not a bad idea. I just to do a talk on this frame, the dynamical content of the Newton's laws, the critical appraisal of the Newton's laws of motion. Are the three laws independent, or sometimes they say that okay, are they really independent or not? They have these questions, right? And this confusion between centripetal, centrifugal force, and non-inertial frames, and Corioli force, and even like Shankar. So basically, you can do to answer to Shankar's question, you can do analysis in non-inertial frame in which you will have forces. Okay. For the analysis,
here is a suggestion.
Go through critically.
Shall we?
Okay. Yeah. Fine. Yeah.
Since there has been things pointed out by Prachi and Shankar, and I'm surely interested. Why don't we have a discussion on this topic next week, maybe led by Rishi?
We can, led by whatever I understand, I can.
Yeah, maybe you can give a small talk and a discussion we can follow, like something like that. Would that help? Is that a good suggestion, or maybe you can complete the discussion now and
No, but I mean, I don't think, I mean, there is anything that I have to say which you guys, obviously, I think it would be all tautology, because it's more from the students' perspective that I'm thinking, because
assume that I am a student.
Sir, can I ask a question, sir?
Yes, please.
I joined on
we completely forgot the
Yeah.
students.
I joined late.
Yeah, please go ahead.
Sir,
Yeah.
So the last slide, in the last slide of the last point,
Yeah.
that is
Yeah.
the acceleration is independent of the dimension.
1 minute.
In the last slide,
Conclusion slide.
the conclusion
Yeah.
slide. The last but one.
Yeah.
Acceleration
And
is
this one?
independent of the dimension.
Yeah.
Then what does that dimension mean there?
Here dimension, I mean R.
Oh.
The length, the length of the
Generally-
cylinder, the radius of the cylinder, and so on.
Generally, when we say such a statement, we mean it whether it is one dimension, two dimension, or three dimension. Here
Okay.
you mean
Here what I mean is the size actually. The size. Yeah. Okay.
the size.
Yeah, size. Suppose you take a solid cylinder of any material or any length or any radius, they all will have same acceleration. That's what the point is.
Oh, any type of solid cylinder, solid or
Any cylinder, you take a wooden cylinder or anything, but it should be a solid. It should be completely filled with material. Yes. If you take a solid cylinder made up of iron, or you take a solid cylinder made up of aluminum or any material of any length or any radius, they will have the same acceleration.
okay. Actually, you can compare this with the Galileo's experiment. Actually, the other thing was it was straight down. Now it is only inclined.
Exactly.
Now it is only inclined.
Correct.
Exactly.
Yeah, exactly.
That's a very
Only
good
your
comment, I
acceleration
think.
depends on alpha. That inclination.
Correct, yeah.
That's the only
That's a very
difference.
good
As you
comment.
see-
Yeah.
As you see in this expression, if you take phi is equal to pi by 2,
Yes.
right?
Therefore, here
It is
also
actually-
the one relevant question comes there. The friction. What about the friction? One person was asking about the friction. Here there will be a rolling
Okay.
friction. Therefore, first of all, you have to define. For example, in the case of a cylinder, whenever that cylinder, it will be always rolling in such a way that axis will be always. You can say that it's always in a particular direction. But in the case of a sphere, if it is rolling, you cannot guarantee that the direction, that particular axis may not be the constant. And whenever that, the other one sir was saying about a cone. The cone, when you say that the cone is moving down a plane, it may not be rolling. It may be having some different process. It may be rolling, it may be jumping, something like that. Therefore, first of all, I don't know whether what you have defined or not, but first of all, you have to guarantee that it always rolls.
Right.
It always
Okay.
rolls.
As far as the sphere is concerned, you have the spherical symmetry, so no issue about it. But
Whichever
for
axis, there will be no problem. Whichever axis
Yeah,
it is taking, there will be no problem.
No problem. But for the cone, I don't know. It will be more.
Therefore,
Complicated.
actually, you have to first guarantee that it is always sliding. Oh, sorry, rolling.
Yeah. Okay.
But actually, that the friction will be, if it is having no friction, can there be a chance that it will be always sliding? If there is no friction, can it be sliding?
It will be sliding.
Actually, no, it
There
is.
was-
It is. If there is no friction, you will only have linear motion.
Linear motion means in this case, because of the gravity, it will be sliding.
Correct.
Yeah. For example, as I said earlier, if you take phi equal to pi by 2, assume that moment of inertia is 0.
No, sir.
I'm sorry.
My
The
question
friction.
is,
Yeah.
my question is, in the case of Galileo's experiment, it is guaranteed that there is no viscous force or any friction is there. Similarly, in the case of this sliding or this rolling, you have to guarantee that there is no friction, no rolling friction.
So
Okay.
maybe could you could you emphasize, I mean, I like your comment, I think I understand, but could you clarify what you mean by comparing it with Galileo's experiments? I
No, in
think
the
I
case
know
of
what you're
Galileo's
saying, but
experiments,
can you
for
clarify?
example, if it is a paper or something like that, there may be some viscous or air drag may be there. Therefore, you cannot guarantee that the same object with a different area, it may not be coming simultaneously. Different area, it may not be
Yes.
coming simultaneously. Yeah, same object, but the area is different. Viscous force may be there. Air viscous force may be there. But in the case, in this rolling, in the case of a rolling body, you have to, in the same pattern, you have to guarantee that there is no, in the case of this body which is rolling, it must not have any rolling friction. Only then you can guarantee that all these things happen with the same equation. If there is a friction, which is a real one, if there is
You
a
are
real
right. You are
friction,
right.
if there is a
Yeah,
real
as you-
friction, your equation will not work.
Yeah, as you pointed out, the friction actually makes the object to make any motion other than linear motion, rotation or something. So that friction
Yes.
is due to the air friction, as you said.
Ah.
So if there is no friction, they will all have the same, acceleration as the Galileo's experiments or anything of that kind, which can be seen from this equation also. If friction is
And
zero,
therefore, if I take that argument to the rolling case, then here also there must not be any friction.
no, it is rolling on a surface, so definitely it has a friction.
It has a friction.
Yes, yes. Because of the surface, you have friction. Yes.
But then the whole equation must be framed in such a way that friction has to be taken into account.
No, friction has been taken care.
But that friction is not coming in any final equations.
No. That is true. Because
Uh.
this friction appears in the form of inertia.
But it's something like a
See
free
here.
fall. It's like something
See,
like
this
a
is like-
free fall. If
See,
it
can
is
you
a
see
free
my
fall,
slide now? You see here, the frictional force is written in terms of moment of inertia.
no, when I compare
Can
with
I make a comment?
yeah.
Yeah, so actually, I think in case of that Galileo's experiment where a feather and a iron ball fall together, there it's a statement about the independence of gravitational force from this the mass of the body,
is that
right?
the Galileo experiment you had in mind, or was it the one that if you let a mass moving, then it will move forever?
I think he spoke about the feather and the iron ball, right?
I see.
Right?
Free fall experiment, free fall.
The free fall,
mass.
but the comparing the feather with the iron ball. That they will both fall with the same G.
Therefore, they strike the ground simultaneously.
Correct. I see. That's not
So-
what I had in mind. Okay.
Yeah,
Okay, go
that's
ahead.
actually a statement on the gravity, as an inertial force. Okay, and that it independent of the mass of the body. Okay, the gravitational thing, the gravitational acceleration is actually independent of the mass of the body, but there is no guarantee that once the rotational forces come into play, they definitely depend upon the moment of inertia, and moment of inertia is a geometric attribute of the body. It depends upon the distribution of the mass. So the torque and hence the angular acceleration and all that is actually a function of the distribution of the mass, and that's why the different bodies with different moment of inertia, they have different accelerations. As you can see, right? As Shankar showed, the hollow cylinder and the filled cylinder and the sphere and the cone, because the geometrical distribution of mass is different. So that's why the torque is different and the moment of inertia is different. Torque is different because the moment of inertia is different, and hence the acceleration is different. So these are two different things,
Yeah, as you pointed out, the frictional force is written in terms of moment of inertia, which depends on the geometry. So as you said, you have a different frictional force for different shapes. Yes. Right?
Ah, yes.
No, frictional force is not depending on the geometry. Frictional force
So,
is-
Then
as you-
I have an issue with that thing because I don't think what we see as the effect of the forces can be considered the origin of the force also. Like frictional force has different origin. It is causing some kind of acceleration that has like writing a mathematical equation in that sense, we cannot say that force is depending on it. Like the origin of that force is something different.
No, but so I didn't get Prachi, what
Like the point is when you write frictional force, the origin of frictional force is the contact between two surfaces.
oh, true.
Maybe it is the weight of the body, mass of the body, whatever is causing that frictional force to come into existence, the contact between the two objects, like that is what is the cause of the frictional force. So it depends on the properties of those materials. We cannot say that it is not, it is depending on, like whatever is the effect, it is depending on that.
Prachi, just one comment here, that as I said earlier, that as long as the frictional force does not attain its maximal value, okay, what different materials will do, the different materials will decide on when is this limiting value of frictional force attained. Because if this mu is small, then of course the frictional force limiting value will attain much quicker. And if the mu is large, of course. But here, as long as you stay within the, lesser than the maximum value of the friction, okay, then the whole purpose of frictional force is only to provide the rotational torque and if you find it about the center of mass, that's it. And to ensure the rolling. Without friction, there is no rolling. That's it. But we are not concluding that the frictional forces, we are not concluding anything about the force from the effect. That's what I'm trying to say.
yeah, I also understand that if there is no friction, there is no rotation, right?
Ah,
Yeah.
Right?
Yeah, it's slide.
That I agree. Yeah, I agree.
It will just slide. So only purpose of friction is to provide rotation, and its properties come into play only in terms of deciding the maximal value. As long as it stays less than that, it is some value smaller than the mu n. As long as it is that, the role of friction is just it is non-dissipative and it just provides for the rolling part. That's it.
But isn't there something that is bothering in this equation, at least it is to me, is that let's say we are having a hollow cylinder. We don't specify what material it is built out of. Its acceleration apparently is fixed. It has to be 0.5 g sine alpha, correct?
Provided it stays, provided it's.
Yeah, I'm saying it's perfectly rolling. It's perfectly rolling. I don't say whether it has reached or not, reached its limiting case or not. And acceleration is fixed. Right hand side seems to be fixed, which means to suggest that whether it is a rubber piece or a metallic piece, the force of friction somehow knows what it should be. It doesn't depend on the material properties. It seems a little not clean to me, that argument. That force of friction typically depends on the contact materials. Here it is depending on the dynamics. And it is surprising.
Can you go to the previous slide, Shankar? Yeah, can you just go to the previous slide? Yeah, one more slide.
One more.
One more.
Maybe this. Yeah, this one. So it is like right hand side is completely dynamical and the left hand side is apparently an interface dependent quantity. It's a little interesting.
But the friction is already determining your acceleration.
Yes.
Okay. So it's not as independent of the friction as it appears, because A,
yeah,
your translational equation of motion, capital F minus small f is m times a. So
apparently, if you have a very icy incline, even then the acceleration will be the same as far as it is perfectly rolling.
that's where the catch is.
Yeah, I agree.
As far as it is
Yeah.
perfectly rolling.
Yeah,
Okay.
as far as it, yeah, let's keep that. Yeah.
So they
So
will
it
roll
seems a
perfectly
little-
at different theta. They will roll perfectly
Yeah.
at different theta.
But still it is bothering. Yeah. That
No,
left hand
it
side
won't
is
roll
a
perfectly.
material.
No. The point is it won't roll perfectly because the theta will be different. Theta will be different.
Therefore, if it is a point object, definitely it will be proportional to g sin alpha.
Yes.
Final equations, you have some constants are there. That constants depends upon the geometry of the object. And in that case, if it is a completely independent of the geometry, you can say if it's a point object, then finally your equation acceleration must be some constant into g sin alpha, g sin phi.
Correct.
Or your 0.71, 0.67, 0.6, 0.5 vanishes, it will be a particular number. It must be a particular number. And it must be g sin phi, independent of the geometry of the shape of the object. If it's a point object,
So
and if
point
it
object.
rolls, if it rolls.
But a point object rolling is not very.
Point object means not a, by definition not a point. It's a point something like a sphere. If it's something like a sphere.
That's
Very,
not
very,
clear.
very small, having a very small dimension, I can say. Very small dimension.
Okay. Yeah. So it's
But
independent.
but for point object, do you define moment of inertia?
Now, theoretically, you can say. Theoretically, you can imagine that all the solid cylinder, sphere, etc., can be considered to be of a single shape. And then if you reduce all these things into a single point, it becomes some single object. And then it must have a constant into g sin phi.
Oh, but then once it's a point object, then there is no rotational equation of motion. There is just translation.
That by definition point object. But I
Yes.
can imagine a practical object. I can imagine a practical. I can make a practical object in such a way that it is neither a sphere, a cylinder, or a sphere. A small object, a very small object which can roll. Then it must be independent of all these things. That constant, it must be independent, and you must get a particular constant.
Which is the sliding case, right?
It is not sliding. It must be roll. It must roll.
Oh,
It must not slide. It must roll.
So since it is independent of the R and all that, it will roll with the same acceleration as long as it's meeting the rolling without slipping condition. Doesn't depend upon the size.
It is dependent on R, sir. That is why the different constants are there.
Yeah.
It depends on the dimension. It actually, if that constant is not there, the constant means that that
The
constants are
constant
different.
is coming from the geometry, sir. Because
Geometry,
I is, so for example, let us write is a beta times mr squared. Okay.
Therefore, that geometry is coming there.
So beta determines the geometry. Mr squared
yes.
gets cancelled, so it is 1 plus beta. G sin phi by 1 plus beta, where beta is determining the factor 2 by 5 by 7, 2 by 3, 3 by 5. That beta determines the geometry.
Yeah.
So it's not the R, but the geometry.
But again, it seems like what we call rolling friction is completely determined by this geometry that we are talking about. In this sense, the beta that Rishi is talking about. So it is not decided by the interface at all. You can have any kind of interface. Isn't that really striking? Or maybe I didn't realize it before.
But actually, the two materials are coming into contact. Therefore, that two material properties, one is rolling and the second one is the inclined plane. Therefore, there must be some connection between those two. That must depend upon, that must change, that will change this acceleration.
But apparently not. This equation tells me that it does not change.
Maybe you are not taking into consideration those things. You are.
Sajesh.
Yeah.
Actually, so as long as the materials will decide what will be the limiting value. As long as it is less than the limiting value, it doesn't matter. The material doesn't
Yeah,
come in the picture.
I understand your statement, but you do agree to the fact that the force of friction, the magnitude of the force of friction, when it is a hollow cylinder, is completely determined by the geometry, not the interface molecules. The molecular interaction does not matter. That's the statement, correct? Am I right? That's the conclusion. I feel that's striking.
I guess one can ask this question, like we have experiments to determine the coefficient of static friction, coefficient of kinetic friction. How is the coefficient of rolling friction actually determined? And ideally, if you read about rolling friction, it is supposed to be, in ideal cases, supposed to be 0 or very close to 0. The job of rolling is to reduce the friction primarily. So
but it
how do we
cannot be 0. Like in this case, it cannot be 0. We just showed it is proportional to acceleration. It cannot be 0. In fact, it's a very high number. Right?
like I'm considering like flat surface, right? Why do we create wheels, right? To create the rolling motion.
We are talking about this scenario. The rolling friction is proportional to acceleration. So it can be a big number. Correct?
It feels like the force, like rolling, the name rolling force is, I don't know, maybe causing some. Like as Rishi is saying, it is just a force. Forget about where it is arising from. Because it is not, I don't know.
Actually, I don't know. When I have never bothered about the, I think when it's rolling, I don't think, at least in Klapner and Kolennikov, they never bother about this distinguishing rolling friction and all that. I mean, as long as you are just as rolling, it doesn't matter. There is some friction and it's not crossing that limit. It's immaterial actually.
But yeah, like, I mean, Rishi, it should bother a little bit because other kind of frictional forces has some meaning, right? Like, even if it is not like a static friction, even if it is not reached the limiting value, you can like clearly tell that it is equal to the applied force. That's why the object is not moving.
Yeah.
Right. And sliding friction has like a clear cut, like clean relation. It is mu sub k times n. But here, I don't know, like what we can associate this force with.
This equation says it is dynamical. Like the motion describes it. Maybe with that open question, we should, like now it's 5 o'clock. I think we should leave ourselves with this open question. Is that reasonable, or should we continue?
Yeah.
I think
it's good to pause and think.
Yeah.
So thank you, Shankar, for
Thank you.
nice
Thank you
talking
so
and
much.
stimulating discussions. Yeah.
Yeah, thank you so much. I didn't expect that, this will instigate so many questions, and for which many of them we don't have clear-cut answer. But there are interesting questions arised, and there are a lot of stimulating discussion due to you and Rishi and other people. Thank you so much. Once again, I thank Shajesh for giving such a beautiful platform to interact after so many years. Nice to see you, Rishi. Thank you.
Yeah. Same here, Shankar. Good to see you.
Yeah.
Can I also ask, the number I see is 09. You could introduce so that.
I am Udayanandan. I am Udayanandan. retired as a college teacher
Okay.
from Kanyangan, in Kerala. it's-
Oh, nice.
Okay.
Nice.
Oh, nice.
I'm staying in Thalassery.
Oh, I am in
Oh.
Thalassery too. Oh, you probably heard, yeah.
Oh,
So,
fine,
Sat-
fine. Okay.
So you spell your name Satyanandan?
Udayanandan.
Udayanandan. Okay, Udayanandan. Okay, great.
All right.
Yeah.
Which
Sir,
college?
you're looking for a college?
Now I am retired. Now I am working in an unaided college.
Okay. Oh, okay.
I retired as a associate professor from Nehru Arts and Science College, Kasaragod district.
Okay. Oh, fine,
Nice.
fine. Yeah, very glad. Yeah. Okay.
Yeah. If you are close by, feel free to drop in.
Right.
This is Chonadam, Eranyoli.
Yes, I know. I am a native of this place.
Yeah.
Lino told me about you.
Yeah.
So I had recommended you to some of my college teachers also.
Okay. Yeah. Yeah. Feel free to just drop by and say hello. That will be nice.
Why can't you have a small write-up of this and mail to us? Whatever you are talking, after the talk, why can't you have a write-up so that in the next session, we can have more thought, we can directly interact with the person who had presented.
Yeah, it's just a matter of work. I mean, we can surely have the slides, I suppose, from Shankar.
Yes,
But a
yes.
write-up
Then
might be a little-
that will be okay.
Yeah, that should be, yeah. Shankar,
I
would you
will
be,
I will send my email ID to you, sir.
yeah, I mean, my email ID is available
Yes, I know your number. I know your number.
Yes,
I will
please.
send by WhatsApp.
Yeah, that will be good. Yeah. And then I will pass this on to all the participants, whoever I know.
Yeah, sure.
Like we had some few participants more, which I don't know them. I have no way to contact them. Yeah. So, yeah, so this will
Yeah,
be good.
maybe
Yeah,
it
this
will
is
be a good idea to ask everybody to type their email ID in the chat, and then you can maybe send later on.
Yeah.
The
I'm not
material or something.
I'm not enforcing anything. I'm afraid that it will spoil the freedom part of the platform. Let it be as simple as possible. Yeah, but I'll surely
Anyway.
send it to you. Yeah.
Yeah, anyway, my email ID is there in the first page. Yeah.
Yes, Shankar, I have. Yes, please. I need it from you. Yeah, and then
it's
I'll
there
pass
in the
it on.
slide. Yeah, for the benefit of audience or anybody who wants to write down. Yeah.
Oh yeah, so can you write it? That'll be better.
Sorry.
I think I can get Udayanandan in case he misses it. I can get it from Linu Kumar. I'm in contact with Linu Kumar.
Yes.
Okay.
Okay, I will be leaving now. So have a nice weekend, rest of the weekend. Thank
Yeah.
you.
Good discussion, I think. And
Yeah.
so for next week, Rishi, can
Yeah,
I
so
request
tell-
you to give a
what
talk or
exactly
anything discussion?
what exactly you want me to like?
You decide. Don't tell me what I want to listen. What do you think we would? I mean, you have attended today, so probably you have a rough idea of what.
Okay.
It's hard to guess who the
Okay.
audience would be, but I think for the last 2 times it has been mostly like professors, probably. Like this is more like it's not really students, but I would say address it to the students, address it to a high school student. I think that's the way I would say it. 11th, 12th standard student, and then we all can participate. I think.
So maybe some okay. I mean, one thought is say a critical appraisal of the Newton's laws, or maybe a discussion on the polar coordinates, and like
Sure.
something like that, something along those lines.
Sure.
Does that
Like I would
sound,
say that sounds good. Yeah. And we can always find interesting discussion around most of these things. Yeah. So,
okay.
yeah.
Okay.
Yeah,
Maybe I
and-
think I'll try and use the what is it called? The tablets.
Yeah.
Yeah, I mean that writing tablets, what is it called?
Oh yeah, that's a challenge with the online presentations. Yeah, this is a slightly different.
Mm.
setup. But yeah, I'm sure you have done this. Yeah, so find a,
Yeah, yeah.
you will find a
Okay.
way, I guess. Yeah. And any kind of
So
presentation. is
maybe
good.
I have to give you some title or something, right?
Yes, we can do that on email maybe or WhatsApp these days.
Yeah, yeah.
Or
So,
you can
yeah.
give it to me now if you are ready.
Let me just think about it and formulate it. And
Yeah,
I'll,
please take your time. It is
Um,
no hurry. I don't try to send it by Monday or anything. Like Shankar's case, I did it on Tuesday or Wednesday, and that's perfectly fine, I guess. So unless you plan to send it to some other people, I think it's okay to send the flyer by Wednesday. That should be okay. What do you guys
perfectly
say?
okay.
Yeah, that should be
perfectly.
fine. Yeah. So we have few days then for that.
Yeah,
So,
really
yeah.
nice
Okay,
to
friends.
Shankar, it was nice to see you because Shajesh, I do still have in touch, but seeing you after a long time.
Yeah, that's right. I was not in touch
How's
with
Amrita
Shajesh for a long
Varshini?
time. Huh?
How's Amrita Varshini?
Oh, Amrita was sitting next to me. Then she got bored and went away.
How old is she now?
She is 14. She's
Okay.
in 10th standard.
Okay.
How about your sons?
Yeah, one of my son is 11, another is 9.
Okay, so fine.
9.5 and
Oh,
11, yeah.
okay, fine.
So
So you are
just
in
for the
Pilani, right?
benefit of others, I should introduce Rishi is a professor in BITS Pilani and Shankar is in NIT Trichy. Linu Kumar is a professor in Gurudev College in Payyanur here. And Venkat Abhignan is a PhD student in NIT Trichy. Yeah. So at least at this point, I know everyone on the screen.
Yeah.
Yeah.
So you're Venkat, you're working in Tiruchi, meaning same place as Shankar, right?
I'm working under Shankar, sir.
Oh,
Yes.
yes.
So if this
Yeah,
helps.
presently he's visiting.
No, I switched on my camera.
Oh, no. I was saying
The audio.
no. I was trying to convey to Rishi
that I am here. Yes.
he's in the same place as.
I am also trying to work under Shajesh. Yes.
Okay, so you are
And that's
visiting
how
the Sphics
these-
Center for Science.
Yeah, and so that's how Sankar sir and Shajesh sir met.
Okay.
So Venkat has this. I think he's the first
Visitor.
visiting researcher in Sphics Science Center.
Yeah,
Okay,
that's
okay.
great.
Yeah.
Good,
Fantastic. Yeah.
Good.
So I wish more events happen at your place. Thank you so much.
Yeah, this
Yeah.
was good. Thank you. Yeah. So
Yeah, thank you all. Bye.
yeah,
bye.
I think we should
Bye.
close.
Yeah.
Yeah. Thank you very much. Yeah.
Bye.
Okay.
Yeah.
Bye,
Bye.
Rishi. Bye, Shankar.
Yeah, it was nice,
Bye,
Rajesh.
Vidyanandan.
Nice sessions. Thanks, Shankar.
Yeah.
Thanks
Yeah,
for the
thanks
good
a lot.
talk.
Thanks a lot.
Yeah.
Yeah, thank you.
Yeah.
Okay. Bye. Yeah.
See you.
Bye-bye.
Bye.
Bye-bye, Linu Kumar.
Okay. Hello. പക്ഷേ ഞാനിത് എടുത്തന്നെ ഉണ്ട് കളരിന്റെ അടുക്ക് നമ്മളൊരു